Hi, it's Dave. I'm going to give you a quick tutorial here on numerical integration of failure rates. For the first problem in homework 4, requires you to find the antiderivative of the log of 1 plus t, and it occurs to me that many of you might be quite a far distance away from your freshman calculus class and may have forgotten how to do that. And the point of this is to remind you that you don't really need to get an exact form solution. You can get an engineering approximation that goes back to the definition of the definite integral, and that can be useful. So from week 2, we talked about the fact that the failure rate was a limit, which you see on the screen, and that the integral of the failure rate, which is the second line, is called the cumulative hazard function, or the cumulative failure rate. And the important part was the third line, which is that the reliability is equal to e to the minus the accumulated hazard, or the e to the minus capital R of t is here. So if we can take the failure rate and integrate it, we can calculate the reliability, and that's the point of the homework. For homework 4, we're given this particular failure rate function, the log of 1 plus t, and so applying what was on the previous slide, what we want is the integral from 0 to t of the failure rate function, in this case the integral from 0 to t of the log of 1 plus x dx. Now that's a Calculus 1 freshman integral using integration by parts, which I'm quite sure you did at some point, but you're probably sitting at home going, God dang that Allwell guy is making me do this stuff, I don't remember how to do it. So you can do it by integration by parts, you can do it by a table lookup, you can use a computer algebra system, or you can take this fourth approximation, a fourth idea, which is get an approximation, and that's what I want to talk about for a few minutes. So you might remember this idea behind numerical integration. If an integral is defined as the area under a curve, instead of calculating that area under the curve, sometimes we can approximate it by rectangles. So we evaluate the function at each of these points. Here we've partitioned the interval from 0 to 2 into 4 bins, and the red line is the function integral of x cubed. So if I look at the left-hand endpoints and I take the height at the left-hand endpoint and multiply it by the width, I get a very skinny rectangle here, get another rectangle here, I get another rectangle here, height times the width, and height at the left-hand endpoint times the width. And if I add up the areas of those 4 rectangles, I have an approximation for the area under the curve, and it's not too great. On the other hand, if I use the right-hand endpoints, here I would have this height times the width, which gives me a skinny rectangle, height at the right-hand endpoint times the width, height at the right-hand endpoint times the width, height at the right-hand endpoint times the width, and I've got these 4 integrals. For an increasing function, the left-hand rule underestimates the area, and the right-hand rule overestimates the area. So there's a nice little compromise, which is to average those two, and that's actually called a trapezoidal rule, because if I average the left hand and the right hand, I get this little trapezoidal area. And that's not a bad approximation, and it gets much better if you have more and more points in your partition here. So that's one idea. It's called the trapezoidal rule. It's very easy to do. You just have to evaluate the function at the endpoints and average. Another rule is, instead of fitting a trapezoid, is to try and fit a parabola to the curve. Again, you've got the left-hand endpoint, the right-hand endpoint. You take the midpoint for any of the little intervals that you have. And then the area under the parabola is known to be the left-hand endpoint plus the right-hand endpoint plus 4 times the value at the midpoint divided by 6 and multiplied by the length of the interval. And that's an exact solution for the parabola that goes through those 4 points, the area underneath it. So, and this tends to be much more precise than using the linear approximation. These are easy to implement in a spreadsheet, and that's what I want to do next, show you how to do that. So let me just delete this out for right now. Clear the contents. All right, so here I've taken the interval from 0 to 1, which is, remember, we want to integrate the log of 1 plus t from 0 to 1. And I've broken it up into just 2 intervals, just in a midpoint. Very crude approximation for the first pass so you can see it. So the value at the left-hand endpoint here is the log of 1 plus the left-hand endpoint. Okay, and the value of the, equals ln of 1 plus t time here. Okay, and then so that's the height, and then the rectangle is the height times the width. For this one, the width is a half, so I'm going to just say this is equal to this value times the height. I'll put the dollar signs in so I can copy and paste this, and that's good. And then if I copy these down, I get the various heights, and if I copy the rectangles down, I've got my choices. So the left-hand rule says that I add the first two rectangles. Let's go back and take I add the rectangles with the left-hand endpoints, which is these two, to get the left-hand rule approximation. The right-hand rule says I add the last two to get the right-hand approximation. The trapezoidal rule says I take the average. So that estimates the area under the curve between 0 and 1 under the curve of the log of 1 plus t to be 0.37. And that's a crude approximation. If I use the trapezoidal, if you use the Simpson's rule, then I take 1 times the left-hand endpoint, 4 times the midpoint, 1 times the right-hand endpoint. I add those all up. I divide by 6 and multiply by the width of the interval, and that gives me a value of 0.385. I happen to know, because I did the integral, that the true value is this number. So these very crude approximations, are giving me results that are pretty close. For my percent error for the trapezoid here is equal to observed value minus the true value divided by the true value times 100. So I've got basically 2% error here. For the Simpsons one, I've got it's equal to the Simpsons rule minus the true value divided by the true value times 100, and that gives me a 0.1% error. Okay, not very bad, especially for simple things here. I can do much better. So in particular, if instead of going from too simple I can have a much finer partition. Clear this out. Okay, I can go 0.1. Let's do it into intervals of a tenth. Okay, and the finer the, gosh darn it. Okay, so that's a much finer partition, and again, I can calculate what the endpoints are for that. And now my width is 0.1, and I can calculate what the area of these various rectangles are. And for my left-hand rule, I can do my right-hand rule, and I can do the trapezoidal rule. Okay, and here it's going to be just equal to the sum of the left-hand endpoints, which go from 0 to 0.9, times the height, which is the area of those rectangles. And the right-hand rule is just going to be the sum of the ones that start with 0.1 and go to 1, because those are the right-hand sides. And then the trapezoidal rule is just the average of those, which is 0.385. When I've got a bunch of these Simpsons rules going now, it would be 1, 4, 1, and then it's 1 again for this endpoint, 4, 1, which makes this middle one a 2. 4, 2, 4, 2, 4, 2, 4, 1 again, okay, because I'm double counting the left and right hand endpoints here. But similarly, I copy down those values, and then the Simpsons rule approximation is just going to be equal to the overall width, which is which is a length of 1 from 0 to 1, divided by 3 in this case, times the sum of all those values. Okay, and that gives me, oops, what did I do here? Oh, times the width of the intervals, which in this case is 0.1. Okay, which gives me my 0.386. So, and that's a pretty good approximation. I happen to know that the true value is equal to 2 times the log of 2 minus 1. So that's from knowing the exact value of the integral. And so you can see that these agree to 1, 2, 3, 4, 5, 6, 7 decimal points. And it's only till you get to the 8th decimal point that you've got a disagreement in what the values are. It's a very, very good approximation. So we want to find the reliability, so we want e to the minus of that number, and that'll tell us what our reliability is. And the percentage error for the trapezoidal rule with 10 is very small. That's just equal to this value minus the true value divided by the true value and times 100. Okay, so that's a 0.1% error, and the percent error here is just going to be very, very small. That's going to be equal to the Simpson's value, Simpson's value minus the true value divided by the true value times 100. Remember, this is in percents, and so it's a tenth, a hundredth, a thousandth, 2/10,000ths of a percent. That's the size of the error between the true value and the Simpson's approximation. So that's a very good approximation. So the point of this is that you don't have to remember how to do the integration. You just have to remember the idea that the integral was defined. The definition of an integral is the definition of a limit of these, rectangular approximations. That's the old Riemann sum, if you might remember from calculus. And then if I take enough of these, I'm going to get a pretty good approximation. So, why is this important? It's important because I've put a problem very similar to this on the midterm, exact same approach but different function, and you either have to remember how to find the closed form antiderivative, or you have to know how to approximate it, or you're going to be dead in the water. So hopefully this helps kick a few cobwebs loose. For the problem on the homework and for the problem on the midterm, this 10 interval partition with the trapezoidal rule, 0.1% accuracy, that's plenty close to give you the get you in the ballpark of the right answer. And the Simpson's rule thing is indistinguishable. So either one will work, or if your calculus is good, you can get the exact solution from finding the antiderivative of either of these. So I hope this helps. I'll put it up on YouTube and on the class site, and I will talk to you on Wednesday.